Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we are going to comprehensively cover material for exam number 1, which is lecture topics number 2 through 7. So this is number 8 as a review of all material for exam number 1. So let's get started. Oops. We began way back when thinking just broadly about where we're headed this semester into Earth's major systems that are subdivided into 4 major spheres here as the atmosphere, hydrosphere, lithosphere, and biosphere, and then thought about these subdisciplines and subdivisions within each of these systems, with the understanding that over the course of the semester, we'll be covering a lot of material that encompasses all of these major Earth systems. And we then went on and did some activities, watched a video or so, and then now here defining these 4 major Earth systems, where we covered the atmosphere, which is the gaseous layer that surrounds Earth, the lithosphere, the solid layer that encompasses the outer skin, if you will, of Earth, the outer 70 kilometers, the hydrosphere, water in all forms, and we'll think of that later this semester, how it forms, where it flows, and then the biosphere, the living portion of Earth, including plants and animals. All right, so then we quickly kind of focused our attention on mapping grids of geographic grids and projections. So let's review. And so we can subdivide Earth into great circles and small circles, where a great circle bisects Earth into equal halves where they pass through the center. An example of a great circle is something like the equator, or every line of longitude, whereas small circles are circles that intersect the surface but not bisect. So they don't subdivide in half like the equator, but noteworthy small circles that we use for our Earth grid reference system include the Tropic of Cancer, the Arctic Circle, the Tropic of Capricorn, and the Antarctic Circle. And so here are lines of longitude, and then next lines of latitude. So lines of longitude are used to determine your relative location or position east or west of the prime meridian. Remembering the prime meridian is this line of longitude running through Greenwich, England. And so our lines of longitude run north and south, and we use them to measure ourselves east and west of the prime meridian. A couple added details: lines of longitude, the greatest distance between 1 and 2 degrees, or 0 and 1 degrees, or any 2 degrees here, 1 degree of longitude, is at the equator. And so that longest distance occurs here at the equator, where there's 110 kilometers between every 1 degree line of longitude. But that distance gets a little smaller and a little smaller and keeps getting a little sequentially smaller as you approach the North Pole, where every single line of longitude intersects, and then similarly at the South Pole. And so it gets smaller and smaller and smaller until effectively, if you're standing right at the North or South Pole, there is 0 distance as they're all crossing right there. Okay, then let's compare that to a line of latitude, where you use the latitude to determine your position north or south of the equator. And so they're also called parallels because all of the lines of latitude are literally parallel to one another. The degrees of latitude increase as you move away from the equator. And so you go 1, 2, 3 to 10 degrees north, 20, 30, 40, 50, 60, 70, 80, all the way to 90 degrees north. So you're going from 0 to 90 north and 0 to 90 south. And that distance then is actually comparatively equivalent between every line of latitude. So between 0 and 1 degree north, it's a 111 kilometers, and then between 89 and 90 degrees north, it's also 111 kilometers. So it's consistent. Another way to subdivide Earth, if you will, into a grid system is within the US, is called the US Public Land Survey. And so this is the primary way that land is subdivided within the US using this cardinal direction grid system. And so the four cardinal directions of north, east, south, and west. And so kind of going through from steps 1 through 4, as we've previously practiced, there's one principal meridian and only one baseline intersecting those named principal meridians. So there's only one intersection, if you will. And so each principal meridian is named, like the Michigan meridian, for example, and there's only one baseline that intersects the Michigan meridian. And then it moves where townships are sequentially getting larger north and then south of that baseline. And so townships run north and south, and ranges run east and west of the principal meridian. And so you're gridding into, for example, Township 1 north, Township 2 north, and then this would be Township 1 east and Township 2 east. And so that grid is Township 2 north and range 2 east. Within each township and range, it's subdivided into 36 1-mile square sections. So each subdivision then is exactly 6 square miles within a township and range, containing 36 square sections. And then within a section, you can move down into sequentially smaller quarter subdivisions where there's only up to 3 quarter subdivisions permitted. And then using those cardinal directions of north, east, south, and west, you think of the smallest quarter to the next smallest quarter, and so on and so forth. So now we need to take a 3-dimensional object, being Earth, and project it onto a 2-dimensional space, which typically is how we as humans are interacting with maps, referencing location on Earth. And because we're taking a 3-dimensional object and projecting it on a 2-dimensional space, then or surface, we need to adjust either size or shape to account for the fact that you can't perfectly put a sphere onto a 2D space. And so some really common projections include the Albers projection, which is an equal area projection that accurately portrays area or size. However, shapes are distorted, and so it accurately portrays size, and then but it distorts shape. And then for the distortion, there's the greatest amount of shape distortion the closer and closer you get to the poles. And so the kind of conversely then, here's one very commonly used projection. There's another commonly used projection being the Mercator, which then maintains correct shape, but distorts the size. And so size is distorted, and then at least similarly, that greatest amount or proportion of distortion occurs near the poles where it's stretched. And so you have this maintaining the correct shape but distorting the size for the Mercator. In the previous lecture topic, we talked about other projections, including the Robinson projection, which is a common, and that one actually does its best to balance both. And so it actually distorts both shape and size, or shape and size, to kind of even each other out. So moving on from, or kind of like connecting and moving forward with grids and then moving into maps here. So a published map should include a scale. And so we can produce or publish maps for different reasons. If you want to look at the entire continental US, that's actually what would be called a small scale. And often I just like to think about it like a fraction. And so a small scale would be like 1/10 million, for example, or 1/31 million. And so a small scale or a small fraction represents a very large geographic area, but it has a relatively limited level of detail, right? We can make out boundaries of states, maybe major features like Lake Superior, etc. And then as it goes down here, we are getting into larger scales, and so our fraction is getting larger, the denominator being not nearly, so from 31 million to 506,000. And then here for some of the maps we looked at with exercise and activities, 1 to 24,000. And so large scale maps represent smaller geographic areas, and they have a much greater level of detail. So we're like zooming way in with these large scale maps. And so this map scale is an actual distance ratio that exists between features on the map and the real world, where you can then use that map scale. And so here, 1 to 24,000, you can measure 1 centimeter on the map and multiply it by 24,000. And then voila, it's 24,000 centimeters in real life. And so we can then use that to actually determine the distance between locations on a map and real life. So there's many types of maps. We're just kind of covering a few types of maps, and we did spend quite a bit of time talking about topographic maps, which possess contours. So a topographic map have contours that connect points of equal elevation. And so these that I'm referring to are isoline maps. And so the lines connect points of equal elevation in this case. The lines connect points of equal temperature for an isotherm map, and then an isobar has lines, and so here these like kind of faint or white lines connect points of equal atmospheric pressure. And we'll think a lot more about this in the next section of the GC 100 course. But I'm going to come back to topographic maps and contours. We did spend some time thinking about interpreting topographic lines, some major kind of outcomes or major considerations of interpreting topographic maps. Where there are closer lines, there's steeper slopes. It's a ridge or a bluff. Where there's wider spacing between lines, it indicates relatively little topographic change over space, so it's flatter. Closed circles represent a hill or a mountain, and then V shapes represent a valley, where the V points upstream. And so a couple more isoline maps, and I encourage you to be able to compare among these types of isoline maps. My favorite, the iso-Hyatt, which then is projecting equal precipitation. And so we could think of precipitation as snowfall or as rain, but either way, iso-Hyatt maps are connecting points, or isoline maps that connect points of equal precipitation. And finally, for this lecture review, last but not least, the isopac map, which connects points of equal sedimentary rock thickness. And we will also come back later this semester to think about the Michigan Basin and the geologic history of Michigan. I can't wait. All right, so how do we collect some of these data? A lot of the data that we're looking at with maps were collected using remote sensing strategies or technologies. And so this measures properties of Earth without direct contact. And so literally it's kind of like taking a picture, because that's one form of remote sensing. However, we can use many different sensors to see the ground in detail. And so we can, as mentioned, we could like literally attach a camera to a plane or a satellite and then take sequential pictures. And that is a form of remote sensing. And then you could come fly over that same area weeks later, years later, or even decades later to then examine. And if that picture was collected over that same exact area, you can assess change over time. So that's an example then of attaching sensors to planes, or now more and more we're using UAVs or drones to collect a lot of these data. However, there is an incredible amount of remotely sensed data collected from satellites. And so I'd like to compare two major orbits or satellite orbits, and they are very different from one another. However, both are widely used for many different purposes. For us as humans, so to speak. And so one type of satellite is the sun-synchronous satellite orbit. And so this is a nearly polar orbit going north to south. And as it goes north to south, our Earth is rotating underneath, and it is quite fast. And so literally, if you start at the equator and then measure the time it takes to get back to the equator, it's only 99 minutes. That's pretty incredible when you think about it, and you think about flying from here to the West Coast or the East Coast, taking many hours. We're thinking about a satellite orbiting Earth in less than 100 minutes. These satellites are very low or relatively close to Earth's surface, so they're only 700 to 800 kilometers above the Earth. And then The nice or the advantage of this, as it goes around and around, the Earth rotates approximately or right at 16 days. It completes that cycle and it returns to the same point above Earth's surface here at the equator, but that path is exactly the same 16 days later, and it's taking that same imagery or that same remotely sensed data, and then it's a little more than 2 weeks, but then 2 weeks later and 2 weeks later, so on and so forth. So you can have this return interval. So compare sun synchronous orbits to geostationary orbits. These are very different in a couple ways, major ways. So in this case, geostationary, kind of like it sounds, satellites remain over the same place on Earth. And so most all of our geostationary satellites literally are directly above the equator. And so they're fixed at a point above the equator, above Earth's surface, and they rotate with Earth in that case. They are very high comparatively. So now almost 36,000 kilometers compared to the 700 or 800 kilometers of a sun synchronous orbit. And again, rotating at that same speed as Earth. So it's a fixed location in space or above Earth's surface at a specific spot. And these are widely used for many reasons, including for us for weather as well as communication. So all of our interactive media then getting interfaced or connecting literally with satellites, geostationary satellites up in space, and then getting sent back down to Earth's surface. There are many types of data that can be collected by satellites, but I just kind of want to focus on a couple major categories of the data we can remotely sense with satellites. And so one form here, we can measure emissivity, which is literally quantifying, measuring the amount of electromagnetic energy that's emitted or released by Earth's surface. We can then create these false color images where we assign a big value, a large value to a red color or a smaller value to a cold color. And so that you can project these data using colors. This is a passive form. And so literally it's only sensing what's coming to the sensor like a camera. It is not that camera or the sensor is not projecting or emitting any energy. However, we collect a lot of remotely sensed data using radar technologies. And so here's synthetic aperture radar is literally a sensor that sends a signal, and then that signal bounces off of something, here in this case Earth, and then that signal bounces and returns to the sensor, and the sensor is actually measuring both the return, the timing, and the angle, and that data of angles and time allows it to interpret, and we can use synthetic aperture radar technologies to measure many things, including speed or weather, for example. Other forms. So we have Doppler ground-based radar measuring local weather, and then we have these large geostationary satellites using different passive sense data. But radar is pretty cool, really, when you think about it. It's this active sensing. So the last slide focused on here kind of satellites is our GPS. Like many of us use GPS, perhaps even every day, or we often integrate and use GPS. And so how does this work? And so within your phone or a dedicated global positioning system device, like a GPS unit here, that unit, your phone or the GPS device, is interacting with satellites up in space. There's networks of satellites. For example, one common network that are phones and GPS units contains a total of 24 satellites that are orbiting Earth in a way that at any given time, there should be at least a few satellites above you in your field of view that your GPS unit, your phone, can connect to. The satellite literally is transmitting pseudo-random code. It's sending out pulses of data, and your phone or the GPS unit literally is receiving those pseudo-random code data. And if it's able to connect with at least 3 satellites, it can interpret that data and use it to literally determine your location north or south of the equator, or east or west of the prime meridian and provide you that GPS coordinate as well as an estimate of your elevation. As these units connect to more than three, so you need at least three to determine your relative location. And if you connect to four, five, or even six, then your relative accuracy or the resolution gets smaller. And so instead of saying you're right here, plus or minus 100 feet, you might be right here, plus or minus 5 feet, for example. And so something to consider again is this is an active form of data transfer where your device is receiving data sent by the satellite. But if that data bounces off of something like a tree, a cliff, or a building or buildings, your sensor, your device doesn't know that there was this multipath error, some deflection of incoming signal from objects like a building causes error in the estimation of your relative position. Okay, so that was kind of that first section on maps and grids and projections. So now we're really going to turn our attention and think about Earth-Sun geometry and then apply that next into radiation, temperature, and atmosphere. So the solar system, let's start there, so we have, for our solar system, we have a sun, which is a star, and then there's 8 official planets orbiting that sun. The Earth is this perfect distance to support life. So like, or unlike in this case, Macho Man Randy Savage, who is too hot to hold and too cold to handle, Earth is not too hot or not too cold. So anyways, returning to our regularly scheduled program here, Earth is almost a sphere. It's actually what's known as an oblate spheroid, where literally it bulges at the equator. You can kind of think of like a ball where you push down, and so it pushes out. So the equator is bulging relative to the distance between the poles. So that is known as an oblate spheroid, where the circumference is greater around the equator and lesser around the poles. Oops. There we go. And so really here, kind of starting our journey, thinking about energy and radiation, but really just simply focusing on sun and sun angles relative to latitude on Earth. And so because Earth is curved, sun's rays don't strike Earth's surface the same because of that curvature of the Earth. And then also soon we'll talk about the tilt and the revolution of Earth. But simply speaking, just the Earth itself, near the equator at low latitude, so near zero, the sun's rays, at least in the middle of the day, strike Earth's surface nearly 90 degrees, so really close to directly overhead. Those have high angles, so near 90. Near the poles, the sun's angles really only ever get like a little bit above the horizon. So when the sun is actually out near the poles at high latitudes, you have low sun angles, like 10 degrees, for example. So low, small sun angles, 10, and then at low latitudes, you have high angles. All right, so we'll come back to, but here to define the subsolar point is the point on Earth's surface where sun angle is 90 degrees and radiation strikes Earth most directly, literally. And then here soon next, we'll talk about the tilt of Earth and the revolution and the fact that that subsolar is effectively migrating north and south as we revolve around the sun. So we'll come back to that, but here the definition directly. And so as described previously here, we're tilted and revolving, and so we revolve in a counterclockwise fashion around the sun, and it takes 365.24 days to make it one full revolution, thus our leap year to account for this overflow, if you will. And then kind of just thinking about this plane of the ecliptic, which is really like the relative position of the sun in the middle and then the Earth, and how we're revolving, and many of our planets here aligned fairly closely to one another with the plane of the ecliptic. I think it's really important to point out that our revolution is not perfectly circular, it is elliptical. So we have an elliptical orbit, and actually the sun is not perfectly at the center. And so there's portions of the year where we're closest to the sun, the Earth here, called the perihelion, and the aphelion is where we're furthest away from the sun. And as we'll kind of come back to thinking about how the role of sun angle and insolation and then temperature, it seems counterintuitive with this slide, but we'll come back to it. But here, just understand that actually in the middle of the summer, we in the northern hemisphere are the furthest away from the sun that we get in a year, whereas in the middle of the winter, at least in the northern hemisphere, then we are the closest, so the perihelion. Right. So if Earth were perfectly perpendicular to the sun and we revolved around the sun would always be directly over the equator. The subsolar point would be directly over the equator, and the poles would literally never receive direct sunlight. However, we are tilted relative to perpendicular by 23.5 degrees. And so that tilt then, and then we're spinning, rotating counterclockwise as well as revolving counterclockwise around the sun. And so it takes 24 hours to complete one counterclockwise rotation. And then at any given time, there's this circle of illumination, which is the boundary between day and night. And so the circle then going all the way around Earth, separating day from night, where the Earth is pointed toward or not toward the sun. So now kind of like bringing some of these concepts forward and moving them into understanding seasons and ultimately understanding radiation and temperature. And so the reason we have seasons, especially as you go further north and south from the equator, is a combination of our revolution and tilt. And so because we're tilted and because we're revolving, again, that subsolar point, which is the point on Earth's surface where the sun's rays are striking at exactly 90 degrees, changes north and south as we revolve around the sun. And so to then tie some of these concepts together, and I encourage you to go back into previous lectures, exercises, and activities, thinking about those University of Nebraska simulators we used to kind of reinforce this topic. But more directly and simply here, the subsolar point is literally directly above the Tropic of Cancer right here during the summer solstice, so on June 21st, and then the subsolar point is directly above the Tropic of Capricorn on, sorry, on the winter solstice on December 21st, so our winter solstice, then Tropic of Capricorn, and then finally, because we're revolving, actually the subsolar point passes over the equator twice every year, and it happens exactly on our equinoxes. And so our equinoxes occur on March 21st and September 21st, and that is when the subsolar point is directly above the equator. Often we think about the sun through our perspective. Literally, we live on Earth and we observe the sun. And so this diurnal cycle of 24 hours where approximately half is day and night. And so depending on the seasons, we might have longer days and shorter nights, or in the winter for us in the Northern Hemisphere, shorter days and longer nights. But either way, it takes 24 hours for the Earth to rotate and effectively demonstrating our 24-hour cycle. And then the celestial dome is this like path, the sun's path relative to the Earth's sky. And so it literally, like, you can trace the sun on the horizon or above the horizon. And so that's what we refer to as the celestial dome. And it kind of really demonstrates that in this picture. The sun rises and it kind of comes up and it goes way up high and then it comes back down. And then that really does change with seasons. So in the summer, your solar noon, which is the highest point the sun reaches on a given day, the middle of the day, the sun might come up here and then it takes this path and it comes up and it takes a really or a longer time in the summer, whereas the winter, that relative position where the sun rises is much different. It takes a different celestial path. And then again here, solar noon is much smaller in the winter when compared to the summer. All right, so now we're going to think directly about radiation, but eventually we're going to put some of these concepts together between Earth-Sun geometry and radiation. So let's dig in. Here's radiation. And so we have shortwave radiation that's emitted by hot objects, and they include gamma rays, X-rays, ultraviolet rays, near infrared, or sorry, visible light, and then near infrared, my fault. And so here is your near infrared. Here is the visible light spectrum, which we see, then going down to ultraviolet, then X-rays and gamma rays. And I don't expect you to be able to specifically define any sort of wavelength for each of these, but I would encourage you to be able to compare between, and so which one of these types of electromagnetic radiation are short-wave forms of radiation and which ones are long-wave forms of radiation. So then beginning at thermal infrared energy, here is the first type of long-wave radiation, which is a form of sensible energy or sensible heat. We'll talk about that later, but here, long-wave radiation that is emitted by objects such as literally Earth's surface. And then we move forward. So thermal infrared, microwave radar, TV, and radio waves are all forms of long-wave radiation. So they have long wavelengths, long distances, or longer between crest to crest, for example. So there's shortwave and long wave. Hot objects like the sun, literally really hot objects, emit greater amounts of radiation than colder objects like the Earth. And so that is referred to or known as the Stefan-Boltzmann law, where there's a tremendous amount of electromagnetic radiation emitted by the sun's surface, whereas comparatively there's much less electromagnetic radiation emitted by Earth's surface, and it's a cold or cooler object. And so quite literally, Earth only emits radiation in the long wave spectrum, largely here as thermal infrared energy, where the sun emits energy across the entire spectrum. And because this is such high frequency, the quantity of energy is greatest with these shorter and shorter waveforms of energy. And so most of the energy emitted by the sun's surface or by the sun itself is shortwave radiation, which encompasses gamma rays, X-rays, ultraviolet, visible, and near infrared. The sun is largely producing energy at a nearly constant rate. There is some variability, but for us on Earth, 99.99% of the time, the amount of energy that's reaching the outermost edge of Earth's atmosphere is constant. And so we call that the solar constant. And literally, it's quantified at 1,370 watts per meter squared. And so at any moment right now, there's exactly 1,370 watts per meter squared of energy from the sun that's reaching the outermost edge of Earth's atmosphere. And so here and moving forward, we're really going to start examining what happens to that amount of energy between the top of the atmosphere and Earth's surface, which is known as our atmosphere. And so it's this medium which radiation flows from the sun on the way to Earth's surface. Our atmosphere has composition, which we'll talk about next, and that the composition of Earth's atmosphere supports life, such as the composition being oxygen and carbon dioxide. And also it provides this protection. It shields us from this incredible amount of electromagnetic radiation, shortwave radiation specifically, that would be really harmful, if to say the least, to life on Earth. And so what is the composition of our atmosphere? We can subdivide the composition into major categories as what we refer to as constant gases versus variable gases. And so a constant gas, literally the level or concentration of these gases remain relatively constant or consistent across space and time. And so if you take the measurement of nitrogen here now and then 6 months from now, or the measurement of nitrogen here versus the other side of the Earth, the concentration is nearly constant across time and space. However, the composition of our atmosphere also contains variable gases. Comparatively, most of our gas that we breathe are constant gases, oxygen and nitrogen here, and argon. So most of the air we're breathing are constant gases, and very little comparatively are variable gases. However, these yet small, these variable gases are tremendously influential on Earth's surface as how they interact with electromagnetic radiation, being some of them, not all of them, but here, some of these variable gases are greenhouse gases. And so let's just focus on a few of these variable gases for a moment. So carbon dioxide is essential to life on Earth through its role in photosynthesis. It also contributes to the greenhouse effect, which helps regulate Earth's temperature because it's absorbing and re-emitting radiation. This is very much a natural process, and carbon dioxide is naturally occurring in our atmosphere. However, in the last hundreds of years, the concentration in Earth's atmosphere, the CO2 concentration, is rising incredibly rapidly and literally in an unprecedented fashion, compared to like 800,000 years of atmospheric records. We'll come back to that later. And so industrial activity is modifying this, and we'll focus on that and what that means later in the course. And so water vapor, so that's carbon dioxide. It's a variable gas. It's a greenhouse gas. And then here, water vapor, it sounds so liquid water that evaporates and turns into a gaseous form as water vapor. And so water absorbs tremendous amount of energy. It is also a greenhouse gas. There is an incredible amount of water vapor in Earth's atmosphere. A very profound and like influential aspect of water vapor is that, like, think about the world's oceans and how much water evaporates from the ocean into the atmosphere, and the fact that that water vapor can absorb radiation from the sun. And now think about global circulation where air masses move across thousands and thousands of miles. You're literally transporting energy over incredible distances where it's literally being stored as water vapor. Another really important gas is ozone. And so ozone, O3, forms largely, it does occur in our lower atmosphere, the troposphere, but we're really here going to be focusing on ozone in the stratosphere. We'll talk about the layers of Earth's atmosphere later. And so within the stratosphere, ozone is most abundant, and it also is incredibly important. It protects us, literally, it shields us from this tremendous amount of UV radiation. And so it is also a greenhouse gas, and it's absorbing an incredible amount of UV radiation. However, when ozone occurs, or if it occurs near Earth's surface, it is considered a form of pollution, as it is harmful to human respiratory function. Okay, so we focused a little bit on the ozone hole, but we're really just going to summarize that quite concisely here, where at some point in human history, prior to 1978, prior to the Montreal Protocol, we were using what are called chlorofluorocarbons, and those were emitted and being released into Earth's atmosphere in the troposphere, where they were relatively benign or didn't have great effect. However, chlorofluorocarbons rose, like literally, went up out of our troposphere into our stratosphere, where they started reacting incredibly with, or like in an incredible amount, with ozone. And so ozone, again, in our stratosphere, plays this really important role of blocking Earth's surface from a tremendous amount of UV radiation. And one chlorofluorocarbon can break down many ozone molecules, and literally, for singularly, that CFC goes and it breaks and it splits ozone, and then through that reaction forming oxygen and and so anyways, dioxide here, chlorine dioxide. And so, but that reaction can occur multiple times. And so one CFC molecule can break down many ozone molecules, being incredibly destructive. And so that depleted our ozone layer and a tremendous amount of UV radiation as a result reached Earth's surface, and it largely forms over, or did form over, Antarctica. And so this happens, or it condenses and concentrates in the spring for Antarctic, where the most amount of this breakdown occurred. And now the ozone hole, as it's known, is closing because through the Montreal Protocol, CFCs have been regulated. And so now ozone levels are returning to pre-affected conditions. Okay, so moving on, particulates in our atmosphere, particles, literally like little tiny particles, are really important. So that composition, microscopic particles carried in the air, both in liquid and solid form. So liquid forms being cloud and rain, and then solid forms, even snow, but pollutants, smoke, dust, ash, pollen, salt spray, etc. But these are also very important as they absorb and re-emit radiation. So the greenhouse effect, the atmosphere absorbs shortwave radiation and it re-emits that stored energy as long-wave radiation. That long-wave radiation then can be reabsorbed by another greenhouse gas or by a particulate, and then re-emitted and again and again. And so it's literally like storing, emitting, storing, emitting. And so it's a form of longer term storage, and that counter radiation, this re-emission and recycling, are multiple steps of emission, absorption, emission, and then absorption, is forming counter radiation, which largely regulates Earth's atmosphere. And so we are very much appreciative of these greenhouse gases. This greenhouse effect is a naturally occurring phenomenon, and it has everything to do with counter radiation. Okay, I'm going to take a quick drink as this is a comprehensive lecture and it is pretty long. So let's turn our attention to heat transfer, where we focus on conduction, convection, and radiation. So conduction is the transfer of heat by collision. And so collision of atoms or molecules, literally directly colliding, is transferring heat. Convection is the transfer of heat through circular movements that literally can happen within liquid, within oceans or lakes, or also within Earth's atmosphere, within the atmosphere itself. So this is a transfer of heat via circular movements, incredibly important on Earth's surface. We'll come back to that. And then radiation directly, like the sun is emitting radiation, and that radiation is traveling through space and through the atmosphere. And so many things emit radiation. The Earth is emitting radiation. You light a fire, it's also emitting long-wave radiation. And so this transfer of heat via electromagnetic radiation. It's the reason it feels hot when you stand in the sun. Speaking of the sun, let's now think about this term insolation, which is the amount of solar radiation, the amount of incoming rays that reaches Earth's surface. And so between space and the surface, what happens to radiation? We thought about it as indirect and direct radiation, which we'll later define. But these indirect paths include scattering and reflection, which is literally a redirection of energy without absorption. Think about light bouncing off of a mirror as an analogy, if you will. And so you have a complete redirection with no absorption. However, there's also a tremendous amount of absorption within the atmosphere that then temporarily stores the energy, but it subsequently re-emits it as another form of energy. And so you receive shortwave radiation, it absorbs, and then it is emitted as a long-wave radiation. And so these have a huge influence on Earth's climate, on the relative amount of scattering versus absorption. Once the radiation does in fact reach Earth's surface, then it interacts with Earth's surface, and we can think about the relative amount of reflection of energy at Earth's surface, and this term is known as albedo. And so a low albedo means essentially no or zero. Albedo would be no radiation was reflected, and a high albedo would mean, or a 1 would mean 100% of radiation was reflected. And so snow has a high albedo, and things like bare earth, like dirt, have the opposite. They absorb a lot of energy. We'll come back to that later. But here, reflection is redirection without absorption versus scattering is redirection, is just a redirection. And so often the subtle difference between reflection and scattering, they're both essentially the same. There is a redirection without being absorbed, whereas reflection often thinks about a return. And so you have this like sharp high angle, where scattering is this more kind of like subtle redirection. So here, scattering and reflection. Now let's think about direct radiation, solar radiation that reaches Earth's surface. And whereas indirect radiation is radiation that reached Earth's surface after it had been either scattered or reflected or absorbed and re-emitted. And so essentially it's just there is some amount of radiation that comes from the sun and it passes all the way through Earth's atmosphere without being redirected and without being absorbed. And so that amount of direct radiation is largely influenced by atmospheric conditions. And then here, indirect radiation, a tremendous amount of radiation also then is scattered, reflected, or absorbed and re-emitted. And so now we had this kind of critical thinking activity where we compared a cloudy day versus a clear day, and really just like focusing on direct radiation simply. Which condition, cloudy day or clear day, do you expect more direct radiation to reach Earth's surface? It would in fact be a clear day, because clouds will both scatter and reflect as well as absorb. And so you would expect more scattering, reflection, and absorption of radiation on a cloudy day, meaning there's more indirect and less direct. And then on a clear day, there'll be more direct and less indirect. So even on a clear day, there's still particulates in our atmosphere, CO2, water vapor. There's still composition of our atmosphere is still redirecting and absorbing. However, comparatively, again, more direct, less direct. Okay, sensible versus latent heat. So sensible heat is the quantity of heat held by an object that can be sensed by touch or feeling. Really, like this is how we often as humans think about heat. It can be measured with a thermometer. However, heat can also be transferred that cannot be measured with a thermometer, and this has to do with the storage and then release of energy when a substance changes state. And so when solid ice turns to liquid and liquid evaporates, there's this transference of energy across these states. And so this gas is absorbing the energy, and so effectively you're releasing energy from water and it's being absorbed as you go right. And then conversely, as gas condenses and turns to liquid, you are releasing energy. So you cannot measure this with a thermometer, but you can mathematically quantify it. And there is an incredible amount of heat, latent heat transfer at Earth's surface and around Earth in general. And so it is important in an energy budget to consider both sensible as well as latent heat. Coming back to forms of transfer of energy. So convection occurs both within the atmosphere as well as within ocean. And so largely when we think about convective energy, we're thinking about sensible heat, literally like hot air rises and then it cools down and it falls back down. And that's what creates convective cycles. And that happens within our atmosphere. Hot air rises, it cools down as it rises, and then it falls back down. And you have this convective cycle. The same exact thing happens within Earth's oceans and large bodies of water. But remember, we have to consider latent heat energy exchanges. And so one way that I like to really appreciate this is this, we can sense and feel this, and later we'll think about wind chill as well as heat index. And then, for example, if it's really hot and dry outside, it is hot outside still, but maybe it doesn't feel quite as hot as when it's hot and humid. And that's because, again, latent heat, there's still energy being transferred to your body literally as it sweats, and then your sweat evaporates, or your body is liquid inside, literally even evaporating through your skin directly. So in both circumstances. And so when it's dry outside, there's a tremendous amount of evaporation, and that evaporated, so vapor, gas state is actually absorbing and your liquid is being released. So your body is shedding energy. And so in this case, there's like a tremendous amount of energy on Earth's surface then being released via evaporation. So it's being absorbed by the gas, and then vice versa as it condenses. And so we'll come back to that and apply that as we think of heat index and wind chill. So coming back just to compare some of Earth's surfaces and their albedo values, snow and fresh snow is incredible. It literally can reflect up to 95% of the energy, meaning it only absorbs 5%. That's pretty dramatically different than something like blacktop, which actually can be about the opposite, where 90 to 95% of the energy is absorbed and only 5 or 10% is reflected. Now you can also kind of move on and compare forest or agriculture land, natural grasslands, buildings themselves, and water, and think about that relative amount of albedo. So now let's kind of hone in on radiation and now start thinking about it at a systems level, like incoming versus outgoing radiation at Earth's surface and Earth as a whole. And so again, as on Earth's surface, we're receiving a tremendous amount of shortwave radiation from the sun. Shortwave radiation being like at the Earth's surface, at least, ultraviolet radiation, visible, and near infrared radiation. And so most of the energy coming into Earth is in the form of these shortwave radiation, so visible, near infrared, and UV. The Earth absorbs, and so does the atmosphere, absorbs radiation and then re-emits it as long wave radiation, and most of that being emitted as thermal infrared energy, which is a form of long wave radiation. Now, to specifically highlight, so greenhouse gases like water vapor, carbon dioxide, and methane are capable of absorbing shortwave radiation. They store that energy and they then emit it as long wave radiation. However, another important aspect of greenhouse gases is that a greenhouse gas can absorb shortwave radiation, but it can also absorb long wave radiation, meaning as, let's say, shortwave radiation comes in from the sun, it interacts with water vapor, which absorbs the radiation, it then re-emits it as long wave radiation, and that long wave radiation can then be reabsorbed by another water vapor molecule, and then again and again. And so these are now counter-radiating energy through the sequential steps of absorption and re-emission. So net radiation is the balance between incoming shortwave radiation and outgoing long-wave radiation. And now we're going to kind of like think about net radiation on a global scale. And so going back to some previous topics that we described, the angle of the sun is so important in terms of radiation intensity. And I really like this figure as it kind of simplifies this. So when you have large sun angles, like near 90 degrees, and if you shine a flashlight down, you have more energy received. And so now just think about like what it looks like when you shine a flashlight straight down. That flashlight is concentrated in this circle. If you then tilt your flashlight lower and lower and lower, literally the amount of distance that is spread across gets larger and larger and larger. And so as sun angles get lower, you're spreading that same amount of energy out over greater distance on Earth's surface, like twice the distance. So it's the same amount of energy spread across twice the space. And so effectively, any one spot in there is now receiving less energy because it's more spread out. this is incredibly important as we think about both seasons as well as climates around Earth. And so low latitudes near the equator receive more energy per unit area because when the sun is out and overhead, it is at or near 90 degrees most of the year, when compared to high latitudes, where when the sun does come out and above the horizon, it's only at this very low angle. Another really major part about high latitudes, especially near the poles, some locations literally have long periods of darkness. So, in terms of amount of energy, duration is also very important. Let's think about that angle and duration here and combine them. So a really kind of cool thing that I think that you wouldn't really guess, but it is true. You can measure radiation using a radiometer. And so in fact, at the North Pole on the summer solstice, which is the Northern Hemisphere's longest day, the sun is only up above the horizon, not too high. It's not directly overhead. It's pretty low on the horizon. But at the North Pole, you receive 24 hours of continuous insulation at a low angle. So at any given time, it's not super intense, but you're kind of on this like low crock pot setting, if you will, and you're receiving a little bit of energy all day long. And so actually, if you quantify that radiation across a 24-hour period, the North Pole receives more radiation over a 24-hour period than the equator on the summer solstice. Pretty cool. And so again, this is combining angle as well as duration. So that's where we have our seasons. And so and we did previously look at this figure where we're kind of combining duration and angle. And so I would encourage you to practice this graphic or review this graphic where now it's color coded as blue, green, red, and yellow, blue, green, red, and yellow, thinking about months from January through May, June, July, all the way back to October, November, December, where our equator at the equinoxes receive the subsolar point is directly above the equator during both equinoxes. And then the equator, really the sun angle in the middle of the day at the equator for the entire year is pretty darn high. And so you're receiving a tremendous amount of radiation at the equator year round. However, over a 24-hour period, there is this like long period of darkness for here at the North Pole, 90 degrees. There's no energy insulation, no energy. And then all of a sudden, beginning at the equinox, you get just this little bit of radiation at the North Pole, but then it rapidly increases. And between March and June, it then gets longer and longer and longer. And again, as a reference, comparing the North Pole on the summer solstice to the equator, the North Pole receives the most radiation on the summer solstice of any location on Earth just on that day or for a short period of time, because even though the sun angles are low, they're up all day long. Whereas other portions of the Earth only receive approximately 12 hours of daylight or comparatively less. So now let's start to kind of integrate this information about global radiation and think about temperature. And so what is temperature? Temperature is a measure of kinetic energy, which I'm always just like in awe of. It's such a kind of a cool thing. We likely, before you ever have read or learn this, like we don't often think of temperature as a measurement of movement. So kinetic energy is motion. And so temperature is a measurement of total kinetic energy of a system or a unit area, as we'll define later. And so heat, then, generally speaking, is this amount of energy in the system. And so when we measure air temperature, we want to make sure that our heat is in equilibrium and there's not this affecting force. And so that's why temperature is measured in an enclosure, because if it wasn't, a portion of your thermometer, your sensor, is receiving direct radiation, it's high energy, and then a portion is perhaps on the dark side is not, and so it's not in equilibrium. However, if you enclose it in a perfect way, allowing good ventilation, you're just recording that temperature of the atmosphere around it, and it's not being affected by radiation. So now, as promised, coming back to thinking about latent heat exchanges and how it makes us feel, literally, if you think about it, and if you've ever watched a weather forecast, they might say in the summer, they'll call for heat index days where it feels hotter than it actually is. And then in the winter, it's kind of the opposite. They'll say, oh, it's going to be 10 degrees, but it's going to feel like negative 25. So let's think about that a little bit. So this has everything to do with latent heat exchanges. So on a hot day, if it's really humid and you're sweating, that liquid water, if it's really humid, there's way less evaporation. The amount of evaporation that goes from liquid into the atmosphere when the atmosphere is already nearly filled with water is not very much. And so literally your body is not evaporating as much, meaning there's less latent heat exchange, and that effectively means there's more energy, literally still inside of you, and your body's trying to shed it. And so there's this low rate of evaporative cooling, and it feels hotter than it actually is. The reverse then, in a way, is kind of true, or is true, where, or with the same concept, because there's high rates of evaporative cooling. So in the winter, when it's windy or winter, it's actually really dry and there's very little amounts of moisture in the atmosphere. And so when it's windy and dry, you have this tremendous amount of evaporation. Literally, your body being liquid on the inside is evaporating at an incredible rate, meaning it's releasing energy from liquid into the gas phase, absorbing that energy, the gaseous phase. And so your body is effectively being rapidly cooled and it feels colder than it is. So now we connect these on more of kind of a geographic or landscape level appreciation, where thinking about things like albedo and land surface conditions and how they influence relative amounts of absorption and then re-emission of radiation. So we can have this urban heat island, which is a human-induced change to landscape that causes measurable temperature increases, meaning above an urban area that's absorbing a tremendous amount of radiation, it's then re-emitting a tremendous amount of radiation as thermal infrared energy, which is sensible heat that can be quantified, and your temperatures above an urban area can literally be several degrees warmer than out away from that urban area in rural areas that have much different and much more natural land use, land cover conditions. Okay, so now we can then also just compare land and water, and then kind of going back to that lecture, there's really four major ways in which radiation interacts with water differently than land. So one is the fact that water is semi-transparent, meaning that that radiation now is being transmitted across, like literally down into the watering column, and it's not all being absorbed right at the surface. There is tremendous amounts of convective movement of energy, radiation, so convective cycling within bodies of water like Lake Superior or the ocean. So that's two, you have this convective transfer of energy. Number three is water has this really high specific heat capacity. It takes a lot of energy to heat water up, at least when compared to something like sand, literally soil. And so because it takes longer, it's interacting with radiation differently. And then last but not least, liquid is 100% water, and then it's evaporating. So you have the most amount of evaporation from liquid to air, whereas there's some moisture in earth, but there's just effectively or comparatively less evaporation. So you have much different amounts of latent heat energy exchanges. These kind of like process-based understanding of how this difference between land and water, so land heats up much more rapidly than water because of these differences, and so that then affects the climates of a region. And so we can actually think about locations on Earth, like the continental US here, we have maritime climates located near a large body of water like the Pacific Ocean versus continental climates, which are areas that are located within a large landmass. Now let's think about that over time. And so because of these differences of sensible heat exchanges, you expect the land to heat up dramatically in the summer because of that amount that is being absorbed by Earth's surface. So a continental location in the middle of the summer should and will likely be much warmer than a maritime location because that Earth is going to heat up rapidly. However, the reverse is true in the winter, which is kind of cool because of that high specific heat capacity of water. Water retains its energy for long periods of time and slowly re-emits it. And so it acts as this like regulatory mechanism. And so now in the winter, you expect now you're like receiving energy from the ocean. And so maritime climates are often more mild or temperate because of that radiation received from the ocean. So you have warmer temperatures in maritime climates in the winter, colder in continental locations, and then bigger fluctuations, continental temperatures being hotter in the summer, and then maritime being cooler because of these cooling mechanisms, because of how insulation can move through, can be convected. It takes longer to heat up. It's also releasing. And so for that reason, in the summer, maritime climates are cooler. And then you just kind of return to winter here where that other pattern returns. Really the same cycle can happen on shorter time scales, like a daily cycle where it will be warmer near the water at night for the same reasons, and then warmer in the middle of the day in a continental location, and then that continental location will cool off. And actually, here in Marquette, we have really kind of a mini maritime effect where Lake Superior, because it's such a big body of water, has that same influence where inland, like in Ishpeming, for example, in the middle of the summer is literally warmer than Marquette. Even if you go up to like Menards, literally in that whole strip, Meyer and beyond, it's often warmer than right downtown Marquette near the water in the middle of the summer. Okay, so now we're approaching the final segment of this Exam 1 lecture review, and we're going to move our way from Earth's surface up to the very edge of the atmosphere as it right before it approaches the outer space. And so we're largely going to think about temperature here in these four major layers, and we'll define each layer. And I do really like this figure. We're going to kind of come back to it here, where temperature is relatively warm near Earth's surface, and then it cools down as you go up and up and up in altitude or up in elevation. And so you have this environmental lapse rate, which we'll talk about next. And so temperature is cooling with the increasing altitude. And then in the stratosphere, it actually does the opposite. It starts warming with increasing altitude. And then in the mesosphere, it goes once again back and it gets cooler and cooler and cooler. And last but not least, we'll talk about the thermosphere. And I really like this graphic here to appreciate the temperature at the very top of the thermosphere is higher than Earth's surface. So I'm going to leave that as a little cliffhanger for you. We'll come back to understand that better here momentarily. But first, let's think about the troposphere. So we have the lowest atmospheric layer in which temperature is decreasing with increasing altitude. So here temperature is getting colder and colder and colder as we go up and up and up with elevation. And that really largely happens because literally we're getting further and further away from Earth's surface, which is literally emitting long wave radiation. So you're getting farther away from a source of sensible heat, of emitted radiation, and then also because of interacting effects with atmospheric pressure. We'll learn more about that in the next section of the course. But ultimately for here and the exam, all you really need to focus on is it is getting cooler and cooler and cooler with increasing altitude. This rate of cooling happens at what is known as the environmental lapse rate, where you could literally at any moment in time estimate what the temperature is 1,000 feet, 10,000 feet above you based upon this rate of cooling. This rate can change a little with the relative amount of moisture in the air, but largely it is very close, plus or minus here, to this rate, environmental lapse rate. Some unique properties, as we previously covered, that we have tremendous amounts of water vapor in the troposphere, as well as aerosols and particulates. All of those are capable of absorbing and re-radiating radiation. So absorbing shortwave and longwave forms of radiation and then re-emitting them, which contributes to what we know as the greenhouse effect, which is a natural phenomenon that we are very grateful for, because without it, it would be incredibly hot in the day, direct radiation, and then incredibly cold, like really cold at night. It would literally, like, we wouldn't know life on Earth would exist without the greenhouse effect. So now let's move on. So as you go up again, it's cooling, it's cooling, it's cooling, and then you can reach the tropopause, which is the top of the troposphere, and appreciate that over time and space, that height of the troposphere can be very different from one place to another or one place over time. It has a lot to do with temperature and hot air convective cycles, hot air rising and falling. And so when there's lots of convection and absorption of radiation and emission of long wave radiation, your troposphere can literally be twice or three times as high in those conditions as often when it's colder. So in the winter in Marquette, for example, often our tropopause is much closer to Earth's surface when compared to the summer. Within our troposphere, there's this unique condition or phenomenon that can occur, not always, but it's when a layer of troposphere occurs where it actually reverses the temperature profile. So we expect the temperature to get cooler and cooler and cooler. And when inversions occur, which often occurs when a cool air mass moves in and sits over top of a relatively warm air mass, it traps this, and in that inverted layer, you actually now have air increasing in temperature within the inversion layer. And then once you get above the inversion, it then once again returns to its normal cooling cycle. For us as humans, while this is kind of a cool natural phenomenon, and in natural areas that don't have large wildfires raging or like volcanic activity, it's not that bad. It looks kind of cool. Here's a picture of an inversion in the Grand Canyon. However, in urban or urbanized environments, like in cities like Los Angeles, Salt Lake City, many of our cities, when inversions set up, it can be really detrimental. It literally suppresses vertical mixing, and it literally captures all of the emissions that are occurring near Earth's surface, and they trap them under that inverted layer. Okay, so now let's go upwards into the stratosphere. And so the stratosphere now is where temperature is increasing with increasing altitude. But why does it do that? Well, it has a lot to do with our ozone layer. So the unique composition of our stratosphere is that it contains a tremendous amount of ozone. However, it contains very little water vapor or dust, especially when compared to the troposphere here. That ozone, remember, is a greenhouse gas capable of absorbing shortwave radiation. And in fact, it absorbs a tremendous amount of UVB radiation, a portion of the UV spectrum. And so because there's ozone, you literally have the most absorption of radiation near the top of the stratosphere, the ozone layer. And so you have the most absorption, the most re-emission as long wave radiation, as sensible heat. You have high temperatures because of all that absorption and re-emission. And as that goes further down and down and down, closer to Earth's surface, there's literally, it's most of that energy has already been absorbed. And so there's less and less and less and less energy being absorbed as you go down into the stratosphere. And that's why then in this case, there's the highest temperatures near the top and the lowest near the bottom, producing this temperature profile. Okay, so you can reach the top of the stratosphere, and that is known as the stratopause, which is where temperature stops increasing with increasing altitude, and it once again starts decreasing with increasing altitude within our mesosphere, which major features of the mesosphere are it is our coldest atmospheric layer. All right, so then we move up into the mesosphere and it's getting colder and colder and colder. And then you can reach the mesopause, which is the top of the mesosphere. And that's where temperature stops decreasing with increasing altitude. And we reach The thermosphere, which is where temperature now, like the stratosphere, once again starts increasing with increasing altitude. And actually, this has the highest temperatures of any layer in Earth's atmosphere. But does it actually feel warm? So let's explore this a little. The temperature is incredibly high. It's literally like considerably and significantly higher in the thermosphere when compared to the troposphere. However, it doesn't feel warm because there's hardly anything in the thermosphere. There literally can be kilometers of distance between singular molecules. And so for us, we sense and feel the emission of radiation from all of the molecules that are all around us. In the troposphere, we have lots of composition. There's all sorts of stuff around us emitting radiation that we feel and sense. However, that one singular molecule at the very top of the thermosphere has extraordinary kinetic energy because it's literally the only thing absorbing radiation. And then that incredible amount of kinetic energy is expressed as high temperature. However, if you were here and that molecule is way over here and it's only one molecule, you don't feel that. So it doesn't feel warm, but it has high temperature. So kind of a unique condition of our thermosphere. And then without further ado, and to end with some very pleasant visible spectrums here, the ionosphere is a layer within the thermosphere, and it's being ionized by cosmic radiation, and that's what produces the northern and southern lights, or southern lights as they're called, and due to this ionization of cosmic radiation within the thermosphere. And so with that, Dr. VG is signing off. Best of luck.